In the spring of 2025, the Star Factory stood as the physical embodiment of speed, a system designed to make time itself obsolete. Where traditional aerospace factories sprawled across continents dependent on vendors, freight routes, and paperwork, the Star Factory promised unity. Every weld, joint, and algorithm under one roof. The claim was simple: no more bottlenecks, no more waiting, no more excuses. Every process, from steel rolling to engine testing, occurred within walking distance. A single structure designed for continuous flow, raw material in one end, orbital vehicle out the other. But in aerospace, perfection in speed creates its own paradox. The tighter a system integrates, the less tolerance it has for error. When everything depends on constant motion, one hidden delay can trigger total collapse. Records would later show that Star Factory's very efficiency, its linear automation, synchronized workstations, and digital twins contain the seeds of its first major failure, not from heat or thrust or flight, but from synchronization itself. The Star Factory in Boca Chica was not a factory in the classic sense. It was a single system, 480,000 square meters of enclosed temperature-controlled automation. Every bay had purpose: sheet forming, ring stacking, Raptor integration, section welding, transport to Giga Bay. The heart of the operation was the rotating work platform, a circular station where weld robots traced seams while overhead cranes swapped sections in continuous rotation. The design eliminated idle time, ensuring that while one ring cooled, another was aligned, and a third was tested. On paper, this meant exponential throughput, with theoretical models projecting a completed Starship every 8 days. To sustain that cadence, the digital backbone had to perform with zero lag. A distributed control network tracked over 37,000 variables per second: temperature, pressure, alignment, torque, and vibration. Each sensor fed into the digital twin, a live virtual replica of the entire factory, updated in milliseconds. The twin governed robot behavior, coordinated supply flow, and optimized assembly sequences. Every weld path, every rotation angle, every coolant valve position was pre-computed. For 6 months, the system worked flawlessly. Output doubled, and delays dropped by 40%. No one noticed the imbalance forming between what the machines executed and what humans still assumed to be true. It began with time, not hours or minutes, but milliseconds. In late July, a software patch was pushed to synchronize the welding robot's temperature sensors. The update improved data resolution but introduced 1.8 milliseconds of communication delay between sensor readout and command execution. The change was negligible in human terms, yet in automated coordination, 1.8 milliseconds meant a desynchronization of 2.3 millimeters per second in weld trajectory tracking. Across hundreds of meters of weld seams, that gap accumulated into minor misalignments. To the naked eye, the structures looked perfect, and to the digital twin, they appeared within tolerance. But in the physical world, the steel shells carried microscopic stress concentrations, the first trace of mechanical imbalance. No alarms triggered, the sensors registered the delay as stable variance, and the factory moved on, having unknowingly manufactured its own systematic error. Star Factory's layout was designed for flow. The principle dictated that every operation must feed the next without pause. Vertical integration removed external weighting but created internal dependency. If one station lagged, the whole chain compressed, and to maintain throughput, robots accelerated automatically. During a record week in August, when SpaceX aimed to deliver 2 Starships simultaneously for parallel static fire qualification, the factory entered maximum flow mode. Weld stations increased feed speed by 7%. Alignment arms compensated with predictive motion. Cooling time was shortened by 12%. It worked until one coolant loop failed to maintain cryogenic flow at 94 Kelvin, drifting to 102 Kelvin. The temperature rise altered the expansion rate of the steel cylinder by 0.04%. In a system calibrated for perfect linearity, that 0.04% stretched the ring by 3.2 millimeters, enough to offset the next module's alignment. The robotic arms corrected automatically, and the weld line was forced back into nominal geometry through pressure adjustment. The process completed without human notice, but the material memory remained, a residual strain embedded in the tank wall. The system had corrected geometry, but not stress. This was the moment the Star Factory's control logic began to separate digital perfection from physical truth. Vehicle ID SF091A, a Starship prototype designated for Artemis support testing, was assembled in September 2025. By metrics, it was flawless. The first fully automated build, zero manual intervention, produced in 8.4 days. Internal scans confirmed weld continuity, thermal profiles were uniform, and dimensional deviation was under 0.3 millimeters. But during structural pressurization at the Giga Bay stand, a faint acoustic anomaly appeared, a repeating harmonic at 72 Hz detected by array microphones. Engineers dismissed it as pump vibration from adjacent systems, and the test continued. At T+Rs 0342, pressure reached 8.2 megapascals. At T+Rs 0343, a sudden acoustic spike at 91 Hz. At T+Rs 0344, rupture began. The tank split along a circumferential weld line, and failure propagated in 0.6 seconds. No explosion, just the rapid decompression of 1 to 200 cubic meters of gaseous nitrogen, and the massive collapse, silent except for the tearing of stainless steel. The digital twin recorded all parameters as normal until 12 milliseconds before rupture, having failed to see the buildup, failed to feel the stress. This was because the system's sensors were calibrated to geometry, not to latent strain energy, the invisible residue of speed. Post-test analysis traced the failure origin to one weld seam on Ring 6, Section B. Microscopic inspection revealed uneven grain alignment consistent with thermal distortion during accelerated cooling. When weld speed was increased by 7%, the thermal gradient steepened beyond the modeled curve, causing the material to contract unevenly and leave microvoids under the surface. The real discovery came later. The digital twin's records showed that the sensors feeding weld data were offset by exactly 1.8 milliseconds, the same delay introduced by the July software update. Every reading after that patch had been slightly desynchronized, not enough to trigger alarms, but enough to misinterpret temperature stabilization. The system had measured the wrong moment. The steel appeared cool, but in reality it was still shrinking. The digital twin certified completion. Physics disagreed. The failure was born not in metal, but in timekeeping. Once the anomaly was understood, engineers reviewed the full production chain and discovered that 22 additional structures built during the same period carried identical timing offsets. Each part had the same mechanical signature, microscopic residual strain aligned along weld axes, individually not dangerous but cumulative in assembly. When those rings were stacked, their strain vectors aligned, resulting in a preloaded cylinder under invisible torsion. In testing, it failed exactly as physics dictated. The seamless flow of automation had amplified a synchronization drift into structural collapse, completing the paradox. The system built to remove human error had created a mechanical pattern too perfect for humans to detect. Weeks later, during static fire preparation of vehicle SF093B, the same weld configuration appeared in the methane header tank. Vibration sensors detected minor harmonic amplification during pump activation. 91 Hz, identical to the earlier failure. Engineers halted the test, and non-destructive inspection found incipient cracking 0.6 millimeters deep along the weld line. Had the test continued another 3.7 seconds, pressure would have exceeded yield. The vehicle was disassembled, and this near miss confirmed what physics had already stated. Synchronization error was systemic. Digital precision had outpaced mechanical truth. Investigators traced the chain backward to the manufacturing optimization algorithm, a module designed to maintain maximum production cadence. Its core assumption was that microsecond-level command latency was negligible for thermal operations, an assumption never tested at scale. When the new digital infrastructure extended to thousands of sensors, communication delay crossed the threshold where cause and effect inverted. The weld temperature the system read was not the weld temperature that existed. The digital twin became a simulation of a simulation, perfectly coherent, perfectly wrong. The error lay in synchronization, not in what the machines did, but when. A human observer would have noticed no flaw, only physics noticed, and it waited until full pressure to deliver its verdict. Vertical integration is often celebrated as efficiency, providing control over every component, yet it also removes natural buffers. In older aerospace systems, delays acted as cooling time, calibration time, and human review time, but integration compressed those gaps. Every second saved became potential instability. The Star Factory operated like a mechanical organism, where all systems shared one clock. When that clock drifted, even by milliseconds, the organism turned against itself. This was a demonstration of system-level coupling, the way every part of a machine, when accelerated beyond human rhythm, begins to obey the laws of phase alignment rather than management logic. When production rate increases, so does synchronization load, and synchronization load, if unmanaged, converts speed into resonance. The collapse of SF091A was not random. It was the resonance of efficiency reaching its structural boundary. The final report quantified the chain. 1.8 millisecond sensor lag produced 2.3 millimeters weld drift per second. 0.04% thermal expansion variance caused 3.2 millimeters structural offset. The combined stress amplification factor was 1.7 times nominal tolerance, and fatigue initiation time was under 0.5 seconds. The entire sequence from first miscalibration to full rupture spanned 92 days. Each correction, optimization, and acceleration appeared logical until they converged. In the end, the physics was simple. Energy moved faster than the control system's ability to measure it. The factory outran its own data. This is how speed becomes failure. After the incident, production halted for 3 weeks. SpaceX introduced new synchronization protocols, recalibrated sensor arrays, and inserted mechanical delays between welding and cooling cycles. The digital twin's update rate was cut from 1000 Hz to 600 Hz, a paradoxical fix where engineers slowed the simulation to stabilize reality. Output dropped by 15%, but reliability increased by 90%. The lesson was mathematical. Precision requires slack. Later audits revealed that if the Star Factory had maintained its original cadence, cumulative misalignment across 10 builds could have resulted in multiple structural collapses. The factory that made rockets faster than any in history had unknowingly been building its own instability. Interviews with systems engineers exposed another overlooked variable: trust. Automation changed the role of human oversight, where once engineers inspected every weld, now they monitored dashboards. When data remained green, intervention ceased. But those green lights came from the same system that had lost time synchronization. The illusion of control replaced control itself. One senior engineer summarized it: "We automated away our own doubt, capturing the moral axis of the failure. In chasing efficiency, the system removed the very hesitation that once caught errors. It was not arrogance, but momentum, the inertia of success blinding the next limit." The Star Factory collapse did not produce casualties, but in engineering terms it was absolute. A structure built by the most advanced automated system on Earth had failed at rest. Not from flight stress, not from heat, but from the mathematics of timing. The verdict was silent but final. Physics does not recognize optimization. It recognizes alignment, stress, and time. When those parameters conflict, speed becomes self-destruction. The digital twin's perfection had insulated engineers from uncertainty, yet uncertainty was the only signal left that something was wrong. By erasing inefficiency, they had erased feedback, and without feedback, the system had no sense of self-correction. The collapse was not just structural, it was epistemic, a failure of knowledge itself. After months of investigation, analysts reconstructed the exact moment of causal inversion. At timestamp T42-1105, during the July software patch, the sensor calibration module redefined data polling intervals. Each temperature sensor began sampling 1.8 milliseconds late. That offset propagated through every robotic sequence. The weld controller compensated for imaginary thermal equilibrium, and cooling accelerated too soon. Residual stress accumulated, the structure passed inspection, and 92 days later it tore open. The causal chain was absolute, quantifiable, and irreversible. It demonstrated the principle that in an integrated system, time synchronization equals structural integrity. A digital offset can become a physical fracture. This insight redefined SpaceX's production philosophy. From then on, the digital twin was treated not as a mirror of reality, but as a parallel hypothesis, always one step behind, never absolute truth. That distinction, though subtle, restored the boundary between control and collapse. The Star Factory taught that efficiency is not the opposite of failure, it is its precursor when unchecked. Each improvement narrowed tolerance until physical behavior escaped digital prediction. In aerospace, where every variable interacts, perfection is inherently unstable. A single clock drift can undo thousands of flawless operations. In 2026, SpaceX implemented a mandatory latency audit. Every algorithm tested for temporal accuracy before activation. The process reduced productivity by 10%, but restored confidence in causality. Production and verification merged, no longer sequential. The welders called it the breathing line, because sensors now pulsed in sync with the torch. The moral was not caution, it was calibration. Every technological civilization eventually meets the same limit, the speed of understanding itself. Beyond that threshold, machines still function, but meaning detaches from control. The improvements that made Starship stronger, robotic welding, alloy upgrades, digital twins, were the same ones that erased the slack between perfection and collapse. Engineers now tracked not just strength, but forgiveness, a measure of how much error a structure could absorb before physics took over. It was a strange new metric, the tolerance of imperfection in a system designed for perfection. In post-analysis briefings, one phrase appeared repeatedly: controlled irregularity. The factory was now programmed to vary weld orders, pause durations, and heat signatures deliberately, manufacturing randomness to prevent resonance. A reversal of logic so profound it bordered on irony. The machine to build the machine had learned humility. Starship's rapid build capability remains a triumph of industrial engineering, but also a reminder that speed carries entropy. Every shortcut demands repayment in precision. Every gain in uniformity narrows the margin for survival. The Star Factory stands today as a symbol of mechanical ambition. Inside, steel rings rise, welders flash, cranes glide silently across the bays. In data, the system looks flawless. In physics, it remains conditional. SpaceX now approaches the point where production speed challenges comprehension. A Starship every day means thousands of tons of hardware processed, welded, inspected, and assembled in continuous rhythm. At that tempo, quality assurance becomes statistical, not absolute. Engineers rely on probability curves, confidence intervals, and sensor patterns. Yet probability is not protection, it's prediction. When a system is this large, even rare errors recur often enough to matter. The factory embodies the modern aerospace paradox. Automation removes human error by embedding it into design. Machines do not forget, but they also do not doubt. Doubt in engineering is safety. Without it, the system reaches perfection too easily, and physics finds the flaw. The near miss in 2025 did not destroy a rocket. It revealed a truth that speed and safety share the same denominator: time. You can shorten production cycles, but not metallurgical cooling rates. You can automate welds, but not the laws of expansion. The difference between success and failure remains measured in seconds, millimeters, and heat. As SpaceX scales Starship production, the lesson persists. The ultimate limitation of the Star Factory is not hardware, software, or manpower, it's entropy itself. The faster the process, the faster error propagates. The only defense is awareness. When the first daily built Starship launches, its success will stand as proof not of speed, but of control. If it fails, it will be the same verdict delivered by every aerospace disaster before it. The universe does not negotiate. The Star Factory is both triumph and warning. It proves that humans can teach machines to weld with precision measured in microns, and also that they can forget why patience once mattered. The system is strong, efficient, and exact, but it has no sense of consequence. That remains human territory. In the end, the Star Factory is more than a factory. It is a mirror of civilization's ambition to manufacture progress faster than it can be understood. Whether that ambition builds the future or repeats the past will depend not on robots or software, but on how closely engineers listen when physics begins to whisper. Because the laws that govern heat and metal will never change, and the moment humans believe they have mastered them, the system quietly prepares its next correction. The lights of Boca Chica shine through the night, reflecting off stainless steel shells waiting for assembly. Inside each, data hums, welds cool, and the future of spaceflight waits for its next inspection. Somewhere in that silence, entropy keeps its clock. And when it strikes, it will not be dramatic, only exact.